Alrighty. Did you guys sign in? All right, I'll take that as a yes. Okay. Yeah, so some announcements before. Um, so- all right. You should be done with lab one by now. And let us know if you need an extension. Just like ping us in your team channels. Um, and also like reach out to us in the team channels if you need any help or come to our lab hours. We'll probably check in with those that haven't finished lab one yet at some point before the end of the quarter. And then also just another announcement, Lab 2 has been released. You can find it in the DAV links channel. And then we'll also be holding another work session next week in the IEEE lab, which is Bolter Hall 2825.
Wait, next week is thing. No,
No,
it's not.
no,
Okay.
yeah, next week. Yeah. Okay. Yeah. So now on to this week's lecture, which is sequential logic. Before that, I'm gonna do a brief review of what combinational logic is. So combinational logic or circuits produce an output that depend only on the current state of its inputs. So if I change the inputs to a combinational circuit, then the outputs change instantaneously. This means that they lack the ability to remember past inputs. So if we look at this diagram on the right, um, if we have these four inputs, it would output one. But then if we change one of the inputs, then the output of this circuit will change nearly instantaneously. And I'll go over why it's nearly and not instantaneously later. So with combinational circuits, then you can't really store any past memory. And so that poses the questions like, how can your computer go back a page on your browser? Or like, how does a video game keep track of your score as you play? Or like a more concrete example that I'll go more into detail later is how can you figure out tomorrow's date if you don't know today's date? And the lack of memory, as I stated multiple times, motivates the need for sequential logic. So take this example. Imagine there's a clock tower at the center of a town. At midnight, when the clock tower strikes, everyone updates their calendar to the next day. So let's just say today's date was November 9th. The clock tower strikes, then everyone updates their calendars to November 10th, which is the next day's date. We can actually represent this in sequential logic and combinational logic. So here we have our calendar, which essentially stores some sort of memory because for like the whole entire day from like 12 a.m. all the way to 11:59 p.m. of the same day, it stores that specific date. And then we have some sort of calculator that calculates tomorrow's date. And this can be done nearly instantaneously. So tomorrow's date is our combinational logic. It takes in whatever the calendar displays and then calculates the next day's date. You could do this, let's say, at like 12:01 a.m. You could also calculate tomorrow's date at like 12 p.m. during the day. As long as you do it before 11:59 p.m. at the same day, then it's all good. And then when the clock tower strikes, the calendar updates to the new date. And so this example, it's very, very similar to how sequential logic works. And yeah, so the calendar is our sequential logic. It only updates when the clock tower strikes. It won't update anytime else. Like you could calculate what tomorrow's date is the minute after 12 a.m. and it won't update calendar's value because you're only updating it during the clock tower. And so this gives the calendar some sort of memory component because you're taking in the previous state as like an input into your tomorrow's date or your combinational logic, and that calculates the next day. And so this brings us to our main form of memory component in digital logic, which are called D flip-flops. So if you look at this diagram, it looks very, very similar to what I drew earlier, which is like a calendar. So in the calendar, you feed in the new date, it outputs that into tomorrow's date and it gets fed back in sort of like a loop. And then here we have a clock tower that indicates like every single time at 12 a.m. the clock tower will strike. And in this diagram, in this diagram, we also have a similar symbol, like which is called the clock, and then we have the D, and then we have Q and Q inverse. Okay, sorry about that. We forgot to share screen. So yeah, a D flip-flop, this is like a very important concept. It copies D to Q on the rising edge of a clock and remembers its state at all other times. This is like probably the most important statement of the entire lecture because that's like what the D flip-flop does. Um, I'll go into more like what a clock is exactly, but for now you can kind of think of it like a clock tower. At like midnight, it will strike, and that's when you copy the value from D into Q. And a D flip-flop stores 1 bit of data. And throughout the entire time outside of this rising edge of a clock or like a clock tower strike, it will output whatever Q is. And it'll only update whenever we have the rising edge of the clock. It will only update the value of D onto Q whenever we have the rising edge of the clock. Um, and yeah, so does anyone have any questions? Because at least this is like probably one of the most confusing parts of sequential logic. And if you get this down, then everything else will be pretty easy. Yeah.
So just to make sure, the rising edge only means when it goes from 0 to 1, but that's like during that transition only.
Yes. Yes, only the transition. And I'll go over more of like what a clock is later and how that why we only want to do in a rising edge. But for now, just think of like the rising edge as like a just like a clock tower strike. Yeah. Any other questions? Okay, if not, we can look at this timing diagram. So a clock, it oscillates between 0 and 1 in like a very systematic fashion. So like here, this is like a timing diagram, what we usually call. It basically shows like what the signal's values are over a period of time. And so here we have the clock that goes from 0 to 1 and then back to 0 to 1 and then back to 0. It oscillates back and forth. Here we have our D value, which as again, as I said earlier, it's the input. And then we have Q, which is the output that it shows. And so this is, if you look at the timing diagram, D is our input and it can change at any time. It can change not at the rising edge of a clock cycle. It can change before, it can change after, but it doesn't matter. Q will only reflect whatever D is during the rising edge of a clock cycle. So like, I think one great example is here, if you can see my mouse. Here Q is always 1, even though D goes down to 0 at some point. But as long as D is not 0 during a rising edge of a clock, then Q will still reflect 1. And we can implement D flip-flops in system Verilog using the following syntax. So here, you guys are probably familiar. There's a module instantiation with the inputs and outputs, and then you have all of your logic inside. So here for D flip-flop, we take in a clock, we take in a reset signal, we take a D. Oh, actually, we don't take a reset signal. Scratch that. We take in a D, and then we output a Q. So what this indicates is that like we always FF represents a flip-flop. It's used to infer flip-flops. It's like similar to like how you use always comp, except you use this for specifically like sequential logic. And then at pause edge clock, that just means that like everything inside the code will be run when the clock has a rising edge. You could also use neg edge, which is whenever a clock has a falling edge, or like when the signal goes from high to low. And then Q arrow equals D, that's called a non-blocking assignment. You guys are probably familiar with just like Q equals D, no arrow. That's called a blocking assignment, which is where assignments are done like sequentially. However, everything inside like this always FF block uses non-blocking assignments. And every sequential logic that we write, we want to use non-blocking assignments instead of the equal sign, which is a blocking assignment. And the difference is that like when you do less than the arrow equals or the non-blocking assignment, everything is updated like simultaneously rather than having some sort of order. Okay, so any questions on like what D flip-flops are or like how sequential logic works? Yeah.
Can you go back one slide?
Mm-hmm.
what is always, can you explain always FF again?
Yeah, so like it's similar to like an always com block, except it's just like you're instantiating different components. So like in an always com block, you're instantiating combinational logic. You're connecting like wires and like gates together. But in always FF, you're using like it's essentially just using flip-flops. They're able to store states. Yeah.
Okay.
Sorry.
So like for always spawn, there's like, was it like begin for always spawn or was it just always spawn?
Yeah, always com. So any kind of block that you use inside system Verilog, you always have to wrap it with a begin and end. It's kind of like how you use curly braces in like C++, where it's like you have to indicate like, oh, this is where everything is inside. Like, yeah. Any other questions? Okay. Yeah, so that was a D flip-flop. These yours last. Okay.
All right. Yeah, so just like one more clarification, like basically for always combination, the code inside that block ran every single time an input changed. So what that means is that every single like all your outputs are based on your input, but this always FF at post edge clock only runs whenever there's a clock. So or a positive edge of the clock. So basically, as you saw in the earlier diagrams, we basically do this where like no, even if the input changes, we only update if the clock is positive edge. So that's basically how that works and what motivates that. All right, so now we're gonna go on to memory. Any other questions? Okay, cool. So memory. So far what we have is we have some kind of like we have some flip-flop that will update its value based on the input as well as particularly whenever there's a positive edge of the clock. However, when we're accessing memory, we don't really want to do this every single time there's a clock edge. So we need to be able to control whenever we access memory. And in order to control when we're writing memory, reading memory, we have to have an enable signal. So as you can see, our little diagram for our flip-flop became a little bit more complicated. So basically, we added a little mux that will say that has an enable signal. So basically, if this enable is on, the input will pass, and if the enable is off, the input won't pass. That's the point of the enable. Yeah, so this no longer forces the output to update every single clock cycle. We can now control when it updates. So here's a little timing diagram. So basically, I'll go through this with you guys step by step. So D is our input, Q is our output, and enable is our enable. So as you can see, our output and our input start at 0. And now we see the first clock edge, positive clock edge. However, when we go down through our thing, we see that input is 1. However, enable is still 0. So that means our output is still 0. We don't update it unless both enable and clock are 1. So now we look at the next positive edge. We see clock is 1, enable is 1. So that means we want to update our output to be whatever our input is. And our input in this case is D, and it's 1. So we update 1 here. So the next one, same thing. We see a positive edge. We see enable is still 1. So that means we need to update our output to match our input. And our input is D equals 0. So that means our output goes from 1 to 0. Is that clear? Do you want me to go through more edges? All right, great. So now that we know how to do this, as you can see here, we've basically been doing this for a single bit of input and a single bit of output. However, what we can do is we can chain along these together and create what you'd call a register. So we kind of touched on this a little bit last time on what a reg is, but now you really know what a reg is and what's inside of it. It's made up of a bunch of flip-flops that allow us to control when to update it, like how large it is based off how big the chain is and so on. So this is our lovely data type. As you can see here, we just have two flip-flops basically strung together. It has 2 bits of inputs, 2 bits of outputs. And one thing to note is the clock is still connected and is connected to the same clock. The point of this is called synchronous design. We don't want our registers and everything to be working at different timing. You can imagine how complicated that would be with like a million registers. you don't want to have to keep track of all that timing. So it's important to keep the same clock throughout. Later on, when we're communicating from devices, you'll notice that we actually have to synchronize our clocks of the devices together so that things work. So keeping a synchronized design is very important. One other note is that there's this Q negated. This is just useful sometimes. However, for our case, you don't really have to worry about it. All right, so now we're gonna, yeah, go ahead. Yeah.
So is a register basically just a bunch of D flip-flops, and then they represent a bunch of bits of number?
Yeah, exactly. So like in lab 1, we had like a 20-bit register. So basically each of those bits is represented by a flip-flop, and that whole register is a string of those flip-flops connected together.
So just 20 flip-flops.
Yeah,
Okay, yeah.
sounds good. Any other questions? Wonderful. So now we're going to talk about clocks and timing. So we've been talking about this clock thing that keeps feeding into it, but what really is it? So as I said, it's used to synchronize how things happen. So this will allow everything to be predictable and stable. So I don't know if we talked about this yet, but basically timing is not always perfect. In reality, we don't have these straight lines. They're like slightly slanted, maybe. There's like delays. So in order to make sure things are all like wonderful and predictable, we keep things based off this clock cycle to make sure we know exactly when things are getting updated. So yeah, a clock signal basically toggles between 0 and 1 in a fixed interval, and it is defined by its frequency and its duty cycle. So as you can see here, I hope you guys know what frequency and period is at this point. So it is it repeats over like a certain frequency. So as you can see, let's just say this little section is 1 second long. So this allows us to tell us how many hertz it is. So we see over this 1 second, we see 4 different cycles. So that means it's 4 hertz. It's 4 cycles per second. And then the next thing about clock signals is called the duty cycle. So the duty cycle is basically what percentage of the clock signal is 1, or what percentage of the clock signal is 0. So as you can see in the first one, roughly half the time is spent at 0, half the time is spent at 1. So it is a 50% duty cycle. Half of it's 1, half of it's 0. In the bottom example, we see it's going to be, first of all, 2 hertz period. There's only 2 cycles in between this 1 second. And then also, basically, there's about 3 times, some amount, 3 times the amount of time that the clock is 0 as it is 1. As you can see, like there's a difference. So it's about 25% duty cycle. So that's kind of how we talk about our clocks and describe them. All right, so yeah, I kind of jumped ahead earlier, but basically, in real world signals, it takes time to travel through the wires and gates. The minimum time for an output to change based off the input is called the contamination delay, and the maximum time is it takes to stabilize after a change is called propagation delay. So yeah, as you can see, there's like 2 paths towards this gate. This one is direct, so most likely it's going to be shorter than this like path through all these gates. So the longest path is propagation, and the shortest is contamination. We typically look at propagation because we like to look at the longest delay in order to optimize things. But yeah. All right. So we have 2 circuits below. This first one, you guys can trace through the gates if you'd like, but basically both of them are ANDing 4 inputs together. So it's A, B, C, D, if you know Boolean algebra. So however, we see that this gate setup has a shorter propagation delay than circuit 1. So this means like that it's probably more efficient. So yeah. Any questions? Cool. See.
Yeah, so like it's important to know that like um you can design like the same functionality for like let's just say here you're doing A and B and C and D, but how you implement it can drastically change how performant your design is.
Is there some relation between frequency and duty cycle or are they like dependent?
Yeah, they're independent. So like you can change the frequency to whatever you want, and you can also change the duty cycle. So like it just ultimately depends on like what you want your
Yeah, I guess you could say like if you want a certain amount of positive edges, like there's like different frequency and duty cycle combinations you can match together to get the same result, but they're like different variables.
yeah. Okay, yeah. So we can trace through this circuit a little more in depth into so like I can explain better why propagation delay matters so much. So here we took our last circuit over here, circuit one, and then we added a register. So or we added a D flip-flop. Um, and what this does, the circuit essentially just flips the inputs of Q every single clock cycle. Here, let's just say if D was 0, then Q inverse would output 1, and then it get fed back into here, and then this would output 1, and then this would update Q to be 1 again, and then this would be 0, and it just keep on inverting itself. And if we look at the timing diagram of this, at every single positive clock edge, we have Q being updated or nearly instantaneously to the clock signal. Here, whenever there's a positive clock edge, Q would update its value. So that's all good. However, we notice that D actually there's a slight delay. So like when Q finishes getting updated, it gets fed through this entire 3 AND gate like circuit. And that actually takes a lot of time. And so D doesn't actually get updated immediately after when Q gets updated. It takes the propagation delay, as we said earlier. And so you can imagine if we have a lot of AND gates connected all in like this similar formation, except there's like, let's just say 20 of them, then D might not even be able to update in time before the next clock cycle. And that creates an issue. And so that's why timing is such an important problem to solve. And yeah, so as I said earlier, sufficiently fast or complex designs may encounter timing violations. So you don't want to drive your clock way too fast such that your combinational logic will take way too long to be updated. So the data that you enter into a D flip-flop must be stable for some time, both before and after the clock edge. And this is because of the nature of how a D flip-flop is, how a D flip-flop works, that we have to do this sort of like setup and hold time, which is the time that you need to be stable before the clock edge, and also the time that you need for the signal to be stable after the clock edge. Here we have like a small diagram which shows what setup and hold time is exactly. So here we have the positive clock edge. There is some X amount of time before the positive clock edge that you have to have your input to be stable, which is just like indicated here. And then you also have to have your input to be stable some X amount of time after the clock edge. And this is the only way you can do so to ensure that the signal gets read properly. If not, then there will be some issues. And what is this issue? What is this issue? This issue is what we call metastability. And so if we have our input, let's just say here, change in between the setup and the hold time, then the D flip-flop might get a signal that is not exactly what we want it to be. And we call this a metastable event because it could be 0, it could be 1, it could be right, but we're not sure. And so we never want to have this in our circuits because then the data that this register or this D flip-flop uses later on will be unpredictable, and that will cause more problems later on in the circuit. So does that make sense? Are there any questions on like timing or why we need timing? Okay. Yeah, and there's a few ways to fix these timing issues that you guys might use. One, very simple, is to reduce the clock speed, because if we increase the time that the clock updates, like here, if we just drag this out to be much larger, then we have more like time for the combinational part of the logic to be updated. Another thing is we can make algorithmic or logical changes in your design. So like here, in this example, we can move this AND circuit to be more of like how circuit 2 is represented to reduce the total propagation delay. And finally, we could also insert registers in between your combinational logic. This is also called pipelining. We're not going to go over this in this lecture, but this is also a very, very common way to reduce resolve timing violations. For the BASIS 3 board, the clock frequency is 100 megahertz, which is actually pretty slow in terms of all FPGAs in general. So you probably won't run into any timing issues unless your design has like a ton of levels of logic. For reference, like usually in industry, FPGAs run at around 250 megahertz to 300 megahertz, so around 2.5 times to 3 times faster. And that can usually sustain around 5 to 6 levels of lookup table logic delay. This isn't like 6 levels of AND gates, it's lookup tables, which are able to withhold more complex designs. And I think we briefly went over what they are in lecture 1. Okay. Should we take a break or?
How much more is that? Wait, how many breaks do you have? 2?
1.
I feel like you just take a break before the system Verilog part.
Okay. Then we'll skip the break for now.
Yeah, we'll give you a break later.
Yeah, we'll give you a break later. Okay, now finite state machines.
All right, so we're gonna talk about FSM. So how do we actually like use all this random jumbo in like our logic and design? So what is a finite state machine? It's basically a model to show certain sequence of events. So each state represents a unique event, and our circuits can only be in one state at a given time. And then we write logic to dictate how things are outputted based off these states and inputs, and then how certain conditions will transition the circuit into a different state. So a quick example for you guys is this FSM for a keypad lock. So in here, we basically have a keypad that will take in 4 numbers in order to unlock it. So in order to unlock it, we will be starting from this reset. So our code is going to be 2468. So that means the first number we need to press is 2. So if we press 2, we'll go to the next state, which is number 1, or like the first state, 1 state. If not, then we'll have to reset because it's wrong. So we'll start from the top again. So now that we got it right, we do the same thing. We go to, if it's the correct number 4, it'll go to number 2. If not, it'll reset and so on all the way up to here, where if we get it right, it will not only reset, but also open as well. Does that like logic and diagram make sense to people? Coolio. All right, so there are 2 different types of state machines. The first one is the Mealy state machine. So this state machine is a type of FSM, where the outputs are determined by both the current state as well as the current inputs. So outputs may change with the inputs, even though it didn't even change in state. So yeah. So here, for example, we have state 0. The blue number here is going to be our input, and the red number is going to be our output. So in this state 0, if we pass in a 0 as the input, we will still remain in state 0 and we will output a 0. However, if we were to input a 1, we would move over to state 1 and output a 0. And you can kind of keep looking through this, see all the arrows. But yeah, so moral of the story, outputs are dependent on inputs and states. State is dependent on what the input you just got was, and you can move through the machine like that. The other type of FSM is the Moore state machine. So this is a type of FSM where the outputs are solely determined by the current state. So what does this mean? Yeah, we just go look at this one. So this is state 0. So once again, if you pass in a 0, it will output a 0. And if you pass in a 1, it will also output a 0. So basically, the inputs are only changing which state the circuit is currently in. It does not affect the outputs. Yeah. That's pretty much it. So basically, to sum it up, more machines dependent only on state, melee dependent on state and input. More tends to be slower, and then melee tends to be faster. More you have to wait for the clock cycle in order to get your output. Oh. There's also typically more number of states required because you'll probably have a lot of different output combinations, so you'll need more states if you're not depending on the input as well. More is synchronous, melee is asynchronous. Okay, I don't know what that means. And then more is typically easier to design since you don't have all these dependencies, and melee is typically more difficult to design. So to kind of practice a bit, we have some example problems. So a coin is tossed until 3 consecutive heads appear. Design a more FSM to describe the process. So I'll give you guys a few minutes. And do you guys think it would be fun if I force somebody to come up here and draw it? Oh, he looks excited. Okay, say less. All right. Yeah, so take some time to think about it a little bit, and then I'll ask somebody if someone's brave enough to come draw it on the whiteboard. Oh, oh, you did? How'd you do that? You can raise your hand if you're done and dying to come up here.
Oh,
Yeah, go for it.
so like more shape machine, are there any inputs at all, or if it's dependent only on like the current state, are there any inputs at all?
Yeah, so here you can see yeah, so short answer, yes, there are inputs. The inputs would be the blue number. So yes, the output is only dependent on the state. However, the input is what decides what state your current circuit is in. So the input just moves it around in the states. Yeah.
So the state depends on input and the output depends on.
Yes, exactly. You joined the same session? Oh yeah. Oh, you did. Oh yeah, there's 2 participants. You bet.
Go back to the.
Which one more, melee? I think you got it. Let me know. Maybe I'll give you a prize. I don't know. You get to have input on what the next food we order is. How about that? Do you want to come up?
Or you can come up as a pair.
Yeah. Um, Don't come up?
Yeah, sure,
All right, let's go. All right,
Hit it up forever.
let's go.
Come on.
Here we go.
I actually don't know if this is right, but.
All good. Don't
Yeah,
worry.
okay.
Right. Okay, so we have, like,
state one, state two. So we start, we have no idea, we have no information at the beginning.
Right.
So this is our first state. Our second state will be reached if we have a head. And then if we have a tails, then it's like we had no information. So we go back to state one. Then we do the same thing. So at state two, we know we've had one head. At state three, we know we've had two heads. If at state two, we flip a tail, then we erase our memory basically, and we go back to state one. Same for state three. And state four is when we know we've flipped three heads. So this is our final state. So yeah. We could do, if you want to represent the output of whether we had three heads or not, you can have 0 here, 0 here, 0 here, and 1 here. Is that right?
Yeah, all like pretty much perfect. One thing is you'll notice during our lab spec, one thing we make sure you guys always do is include a reset button, just in case like things go to trash. So it's always good to like bring this back to the start. But yeah. Or I guess this is 0 and 1. Yeah, that's good. Good job. Congrats. If you want food, you can let me know. I don't know. All right. Skip the room. So do you have time? Okay. We're gonna skip this example. You guys can try it out if you like. It's a little bit more involved. So this next one is so quickly go through this. Give it a minute or two, and then I'll explain it.
Right, it's a little cut off, but it's asking like, is this timing diagram a mealy or a Moore state machine?
All right, so I'm just gonna continue on for the sake of time, so I'll just explain it really quickly. So, the answer is more. To be honest, not the biggest fan of this diagram, but basically on this clock edge, we see that basically there are going to be a total of 2 bits to define the state. That's why there's like 2 lines here. So as you can see, these 2 lines are just kind of switching between these 2 states. So as you can see here on this first clock edge, there's a switch in the state. And likewise, there is a switch in U. However, this doesn't really reflect what happened in input. Same thing for the next clock cycle. There's a switch in the state. However, like, U changed as well. You can kind of follow the pattern, but basically it seems like whenever there's a clock edge and the state changes, the output will change. So as you can see, it's only really dependent on the Moore. However, there's not really a pattern between the inputs and the outputs. Yeah, you can look at them more if you'd like.
Okay, yeah. So how do we realize finite state machines in digital logic? So usually what we like to do is we have D flip-flops or registers that store the states. We can represent them using just like zeros and ones. So like 0 for state 0, 1 for state 1, and whatever, and you can encode them however you like. And then you pass in all of these S values, or like the state output values of these registers, feed them into a combinational logic, which you call next state. And that calculates like what the next state is based off of what your current state is, and also some form of input, which we can call X. And then after that calculates the next state, we feed them back into our registers and update the registers on a positive clock edge. And we follow this exact design format when we write Verilog. And so in system Verilog, you could write state machines in many different other ways, But to make it as readable as possible for other people, we typically like to write it in the following format. So first, rather than representing the states in just like zeros or ones and like it's like very confusing to understand, we'd like to define some sort of like enumerator to like replace the numbers with some form of like variable name so that it's easier to understand. So here you could have like state idle, state wait, state done, even though they're represented actually in bits, we could rename them to make it easier to understand. And then we instantiate a state and then also a next state. And then we have an always FF block that updates based off whenever there's like a positive clock edge, or like an asynchronous reset, which Gerard iterated earlier, which saying that like reset is very important. We usually always want to have resets in our sequential designs. And if there's a reset button that's being pressed, then state will get updated into idle, else then state will be updated into whatever the next state is, which is like very similar to what this logic diagram does. And then after that, we have our combinational block. Our combinational block then calculates what our next state is based off of what the current state is and also what like inputs are being given. And we usually do so using a switch statement. In System Verilog, we call it like a case. So here you see that there's like a case. If it's S idle, then you do whatever. If it's S wait, you do whatever. And if it's S done, then you do whatever. And then usually you always want to have a default case in the off chance that your state is in a wrong place. And then finally, we have some form of combinational block to calculate the output. So here it's very, very simple. We just have another case statement. If you're in this state, since this is like a more state machine, the output is purely dependent on what the state is. So if it's idle or wait, then the output is 1. If it's done, then it's 1. Sorry, if it's idle or wait, it's 0. And then if it's done, then it's 1. You can go back in the lecture and you'll see all of the parallels between how we do it in the logic diagram and also how we do it in System Verilog. But this is the easiest way for other people to understand it. Are there any questions with this? Okay. Okay, thank you. Well,
I'll just record that.
yeah. Okay. Okay, yeah. Sorry about that, but that's it for lecture. I'll post a recording about test benching. Hopefully that'll be.
Yeah, that was the last section we had.
Yeah,
So we'll just record that one.
So now I'm going to go over the basics of test benching. So first, what is a test bench? A test bench allows us to verify the functionality of one of our designs through simulations. It's essentially a container where we feed inputs that we want into the module and then that we want to test, also known as the design under test module, and verify that the outputs of this module are what we expect. So for this tutorial, let's just consider a very basic adder module, and we are going to be test benching this simple adder module to make sure it's being implemented correctly. In this case, simple adder would be our DUT or design under test module. So to test bench simple adder, we need to make another module to feed simple adder with the inputs and also output the outputs. By convention, we usually call this test bench module the module name that we want to test _TB. Note that this module should not have any input or output ports. Instead, you declare all your variables inside the module to feed into our design under test module. So below is an example test bench skeleton to do so. Now I'm going to go over how to do all of this in Vivado. So first, what you like to do is to create the simulation source. Here I've already created all of the files and set up the project for the test benching. So on the top left, click the plus, click add or create a simulation source, click create file, name it simple adder TB. Remember to make it System Verilog, click finish, and then click OK. After which, under the simulation sources folder, you should see your new simple adder TB. Now, note this timescale variable or line of code. In the past, we've told you to ignore it, but now this timescale line of code is actually useful. So what does this actually do? At the top of every test bench module, we want to add this timescale because it helps the test bench know what unit of time we're working with. So on the left, our 1 nanosecond or 1 ns, this represents our time unit. And on the right of the slash, this represents the precision that we're working with. So if we have 1 ns slash 1 ps, then we're essentially saying that we're working in, our time unit is 1 nanoseconds, and the precision that we're working with is 1 picosecond. And what is time unit? So that determines the unit of time for all of our pound commands. So if we have pound 5, then that just means we're delaying it by 5 nanoseconds in the test bench. If we have pound 10, then we'll wait for 10 nanoseconds if we have a time scale of 1 nanosecond. What this picosecond or like this precision means is that like we could say pound 10.52 and it won't round to the nearest nanosecond. Instead, it will round to the nearest picosecond. After that, we want to actually start to add all of our signals. So if we go back to our module, remember, don't put them into the input or output, put them inside the module. So here, let's instantiate our signals that we want to feed into our simple adder module. If we look at simple adder, we see that here they have A, B, and sum. And so now we just need to create our test bench to match that. So let's create our first signal, the signal that we're going to feed into A. And then let's feed in our second signal, which is going to be B. And then finally, we want to look at the output of this. So let's call it TV sum. After we create our signals, we want to feed these signals into our simple adder module. And we want to instantiate this simple adder instance. So let's do this very quickly. You guys are probably already familiar on how to do this. Again, reminder, this is the module name. This is what we want to call it. Usually by convention for test benching, we call the modules that we want to test DUT. And then we feed in the inputs. Great. Okay. So now that we have all of our inputs, we've instantiated our module, now we actually need to drive the inputs. So how do we do that? We use an initial block. So an initial block is just the initial keyword and then within a begin and an end. And everything inside the initial block will be run exactly once at the beginning of the program's life. Usually when we synthesize stuff onto an FPGA, we can't use this initial block because it's not synthesizable. It doesn't really make sense for you to tell like an FPGA to like, oh, at the beginning of this program, do whatever this. Usually we use a reset signal to indicate that. And so just remember that initial blocks are only used for test benches. They're not used for any modules that you want to synthesize onto an FPGA. And within this initial block, we can now actually add our test cases. So let's just say our first test case, we want A to be 2 and B to be 3. Then we just write TBA is equal to 2, and then TBB is equal to 3. And now this is where our time scale comes in. We want to use a pound 10. This represents 10 nanoseconds of delay. So after 10 nanoseconds of delay, we can now set our second set of test cases. Let's just say if our test case is A is equal to 5 and B is equal to 1, then we expect our output to be 6. So after we add our second test case, we want to add this like separator again, which is like our delay. So we add 10 nanoseconds delay. And then finally, let's just add a third test case. Here, let's just do A is equal to 9 and B is equal to 8. And then we add another 10 nanoseconds of delay. After we're done with all our test cases, we usually use the finish keyword to indicate that our test bench is finished and to tell Vivado to terminate the program. And yeah, that's pretty much it. That's the entire test bench. Obviously, there's going to be more complex stuff when we get into sequential modules. I'm not going to go over this in this tutorial, but I've included some slides on how you can do so inside lecture 3. So now we're going to actually run our test bench module. On the left here, we see this simulation. So we just run simulation here, click run behavioral simulation. After you give it a while, it should finish simulating, and you should be brought to this page. Here, it's usually called like something like untitled. This is going to be our waveform. So what our waveform is it indicates how many, like it shows like the timing diagrams of our modules in our test bench. This is the exact same timing diagrams that we've showed in lecture 3. And so like here, since we've made 10 nanoseconds of delay and another 10 nanoseconds of delay and another 10 nanoseconds of delay, we have a total, our whole entire test bench takes 30 nanoseconds to run. And so you can see here, it says 30,000 picoseconds, which is 30 nanoseconds. So to zoom out and to like see the entire test bench, we usually click this zoom fit button on the top here. Then it will just scale everything correctly, and you can clearly see here that our test bench module has correctly fed in the inputs to our simple adder and also read out the sum. So here we can look at our first example here, 2 plus 3 is equal to 5. Our second example is 5 plus 1 is equal to 6. And finally, 9 plus 8 is equal to 17. Note that this is in hex, so it's 16 plus 1. And yeah, that's all you need to do make a very basic test bench. So as I said earlier, with sequential logic modules, you usually want to instantiate a clock. So this is the typical notation that you want to use to simulate a pseudo clock signal. What this does is that here we have our initial block, we instantiate clock to be equal to 0 at the beginning of our test bench, and then forever, every 5 nanoseconds, your clock will invert. And that's how we create this clock signal. Besides what I've showed you here, there's also a lot of other useful system Verilog system tasks and functions. If you look at your Lab 1 test bench, you'll see that actually a lot of these are actually used. So for displaying and monitoring, we have the display command, which will print a formatted string into the console with a new line. For the write command, we print the string without a new line. Monitor prints a formatted string whenever a variable changes. Time returns the current simulation time. And then we also have some simulation control commands, such as like finish, which we've used here, which tells the simulation to stop and exit. And then stop just essentially adds a breakpoint into your simulation and sets you into interactive mode so that you can look at what variables have, what values certain variables have. And I've also linked a really good resource here that goes over more of what system tasks and functions, useful system tasks and functions there are in System Verilog. But yeah, other than that, that's the end of test benching.